Hi everyone, 4.9 at the end of chapter 4, antiderivatives, is going to be chunked together with chapter 5. We are taking a look at undoing essentially all of the work that we've been doing in chapters 3 and 4. So for this warm-up, I'm going to show you what the antiderivative would be really quickly, and then I want you to pause the screen and see if you can come up with what the rule is. So, definition, antiderivatives, a function, capital F of x is the notation, is an antiderivative of little f of x on AB if the derivative of big F is equal to little f for all x belonging to AB. So if we can derive capital F, derive the antiderivative, and return to what we started with, then we have a true antiderivative. So the process of finding an antiderivative is called integration. The notation that we use for integration is as follows. So the indefinite integral, meaning without bounds, is the integral, this is your integral symbol, of f of x dx. The dx is there as a notation showing that we are integrating or anti-deriving a function that was previously derived with respect to x in this case. And it's going to equal capital F, or the original function, plus c. Okay, I didn't put the plus c in the warm-up. It's something that I want to talk about here, but the c is important. It means that the derivative of the original function is equal to little f, or the derivative technically. So we're working in the reverse direction that we did before. So your power rule, this is what you could have discovered in that first warm-up page. If we are anti-deriving or integrating x to the n power, we will be adding 1 to our exponent and dividing by that new exponent, or multiplying by the reciprocal. And then we add c. We add c for that unknown constant that might have been there in the original equation that would have derived to 0. Okay? And this power rule works only for values where n is not equal to -1, because if n is equal to -1, we really have a natural log scenario. So back to what the warm-up page was, just do the first one for you. If we integrate x cubed, dx would be the proper notation. Right, we add 1 to our exponent, and we divide by that new exponent. And we add c. So that's what the rule states. Or you can, of course, write it as 1/4 x to the 4th plus c. So add 1 and divide by the new. Right? It used to be multiply and subtract. Our sum rule and our multiples rule, very, very similar to what we saw in the beginning of chapter 3. Essentially, it's saying that you could, quote unquote, distribute the integral symbol to each individual term. You could pull out coefficients if you so wanted. But of course, you don't have to write it that way. You can just go ahead and integrate or anti-derive each term individually. So the 3x to the 4th would become 3x to the 5th divided by 5, minus 5x to the add 1, so 5/3, divide by 5/3. You don't have to try to do all this in your head. Write it down exactly as the rule states. Plus x to the -2nd, divide by -2, plus c. And then you would want to rewrite this, clean it up as much as you can. So f of x, capital F of x, equals 3/5 x to the 5th. 5 divided by 3/5 would be 5 divided by 5/3 would be 3 times 3/5, which is just 3. X to the 5/3 minus 1/2 x to the -2nd plus c. Okay. So I'll leave this next example for you to just try on your own. There's a lot of rules in this section, so I don't want to take too long on the video. On this page, I just want to point out for our notes that if it's starting as a product rule, we don't have a rule for product rule with integration. You want to go ahead and distribute this to x cubed minus 4x dx. which then would antiderive or integrate to x to the fourth divided by 4 minus 4x squared divided by 2 plus c, or 1/4 x to the fourth minus 2x squared plus c. Okay, other rules that we want to antiderive: if the derivative of sine is cosine, and therefore the integral of cosine is sine, right? It works backwards. If the derivative of cosine was negative sine, then the integral of sine is negative cosine. Okay. So this one would become 3 sine x plus cosine x plus c. I tend to keep these memorized in the derivative direction and then kind of switch it in my head when I'm integrating. So this one becomes negative 2 cosine x plus sine x plus c. Again, always slow down or pause my videos to make sure that you're fully understanding. I know that sometimes in the video I'm going faster than I would in class. Here's those other rules, right? So tangent derived to secant squared. For regular calc, these will be provided to you, but for A, B, and B, C, they would not be provided to you, so I'm crossing that off. So tangent derived to secant squared, therefore secant squared integrates the tangent, etc. You can't integrate something that you didn't have a rule that previously derived it, okay, if that makes sense. I'll add the sine and the cosine to this page. So here's your 6 trig rules. So 5 secant squared dx would integrate to 5 tangent x plus c. 4 cosecant x cotangent x would be returned to negative 4 cosecant x plus c. Right, so what I meant before, I couldn't integrate tangent and automatically have an answer for you because there wasn't a rule that gave me an answer before of tangent, right? I know how to derive tangent, but I didn't have anything that derived and gave me tangent. So therefore, I wouldn't be able to antiderive it. Okay, I'll leave these to do in class or as extra practice for you right now. And then let's take a look at reversing dx over x, or 1 over x, or x to the negative 1, however you want to write this. It will always integrate back to ln of x. The absolute value symbols are important because you cannot take the ln of a negative value. So they're necessary in order to make this possible. So anytime you have an x to the negative 1 power, it returns to an ln. E to the x always derived and stayed the same, so same thing. It antiderives or integrates and stays the same. So this example would become 2 ln, absolute value of x, minus cosine x plus c. This one will become 3e to the x. Minus 2x is just a linear term, it's fine. So minus 2x squared divided by 2 plus c. And the last one, 2e to the x plus 4 ln, absolute value of x, plus c. Okay, so here is the beginning of what I refer to as a linear chain rule. Later in this chapter, we will learn the chain rule in its entirety for the integration process, but for now we're just looking at a linear chain rule. Right, so what this is saying is if you have an mx or a kx plus b as your input, and this will work for ease, it will work for trig, it will work for anything, any linear chain rule. So we have a composition where the inside is just of the kx plus b format. So when we had a linear chain rule with the derivative direction, we would multiply by the inner prime. So to undo that, we're dividing by the inner prime, and the inner prime of something linear is just the slope, just the k. So that's where that 1 over k coefficient came from. That's what this rule is doing, dividing by inner prime. And later in the chapter, basically that's what happens when we are doing the chain rule. We're dividing out that inner prime, but it's more complicated than just a k. So for now, what we'll be able to integrate these types of problems, this would become 12e to the 7 minus 3x divided by that negative 3 plus c. So negative 4 e to the 7 minus 3x plus c. The thing that I like about this section, this unit, is we've gotten so strong with deriving, so whenever we arrive at an answer, if we're not sure, we could derive it to confirm that we get back to what we started with. So down here, if I were to take negative 4 e to the 7 minus 3x plus c and derive it, right, I would still have negative 4 e to the 7 minus 3x. I would multiply it by negative 3, and the c would go to 0, which of course the negative 4 and the negative 3 equals a 12, and it confirms what we started with. Okay, so here's those linear chains again with your trig. Works exactly the same way. And I'm going to write this more generally. If we're integrating any function where it's kx plus a b in there, it will always become the original with that linear input divided by k plus a c. It's only going to work for linear chain rules. So this example goes to negative cos of 8t minus 3. The whole thing gets divided by the 8. And this one goes to plus 20 sine of 9t, whole thing divided by 9, plus c. And go ahead and check it with differentiation or the derivative if you'd like to. Okay, some practice problems I'll leave for class. Another tangent line problem. I'm also going to leave this for class. I want to make sure that we do this together, so make sure you ask me about this one. Okay, so this last one I want to do together. This is something that allows us to figure out what is that unknown c. If we're given an initial condition, then we can figure out what the c value is. So right now we're given a derivative, an initial condition for the original function. So if I integrate the derivative, right, then I end up having 8x to the 4th divided by 4 plus 3x cubed divided by 3 plus c, or 2x to the 4th plus x cubed plus c. And that's my original equation. Now, if I know that when x is 2, the function equals 0, then I can evaluate and solve for c. And c in this case ends up being 32 plus 8, or negative of that. So we have a negative 40. So my original equation is 2x to the 4th plus x cubed minus 40. So you need to be given a starting point in order to come up with the c value. Those are considered initial condition problems. Here's another one that I definitely want to do together. This would be a double. So I'm given the second derivative, the first derivative information, and the original information. So we have to go through this process twice. This is something I want to do together.